great pleasure to welcome Martin Odersky, who is going to give the keynote today. So I'm sure many of you know Martin, or Martin's work at least, going back many years. He is most well known maybe for early work on Java, where he is the one of the inventors of the design for generics that got adopted by Java. But of course, you'll also know him for the programming language Scala, which combines ideas from functional programming and object-oriented programming. And it celebrated its 20th birthday in January. And it's become, I mean, so popular that apparently they've named an opera house in this city after it. But so it's anyway, it's my great pleasure to welcome Martin, who's going to give a talk today.
Thank you, Andrew. Thank you for the invitation. It's a pleasure to be here. So what I want to talk about is some recent work we did on capabilities. And here I want to talk specifically how we can use capabilities for control effects. And I should say this is joint work with a lot of people, some of them my PhD students, former PhD students, collaborators. You see the list here at the bottom. So to start with, functional programming has won, right? Yay. For instance, if I look at the Scala community, I see that there are really very impressive, massive code bases, for instance, at Netflix or Disney Plus, that drive their event processing backbones, using essentially effect systems, monad stacks to do that. And those effect systems are in widespread use, and we've seen over the last 5 years probably a shift in Scala usage from being sort of a more Java-like, Java without semicolons, as people sometimes say, to really full functional, purely functional code bases with referential transparency and staged effect systems and all that. But on the other hand, there are troubles as well. Has it really won? The problem is that these systems, which now are in long-standing 5 to 10 years industrial use, typically terrify newcomers when they come to and say, oh, this is really hard. This is not what I used to. And I believe after 15 plus years of that, where we have employed these systems, these effect systems, it's not just an education problem. I think there is something more serious going on. So what I would like to avoid is the image of functional programming as essentially you need to be a category theorist with a PhD, otherwise you don't understand any of that stuff. So basically I want to avoid the image that you have to be an ICFP attendee to understand functional programming. Functional programming should be much, much simpler than that. I think we all agree on that. And so to give an instance for that, early this year the Twitter code was open source, so people could look at the whole Twitter source, which is written in Scala. And I saw this tweet here, it said, my biggest takeaway from the Twitter source so far is that Scala is surprisingly readable. Yay, that made my day. But then there was a response to say, yes, it's certainly used in other corners of the world by hardcore FP people, where the readability is more questionable though. So that's not good, right? That's not good that functional programming has this image. So if you look at what an effect system is, then it's essentially a staged program. So we have a computer. Computers can do lots of things. They can handle errors. They can do network connections. They have state, transactions, resources, the file system, everything. If you write to the computer, then you have a lot of capabilities. In functional programming, we say, well, we shouldn't use all of these things, at least not directly. We want to be in this box with the lambda, which says, well, this is pure functional programming. There are no effects, there's no resources, and things like that. So to get all the rest, we stage things. We produce a program, a purely functional program that has as its result an effectful computation, as staged programming. So all effects are handled in the second stage, and the typical way to do that is to use monads for composition. Okay, so the problem with that approach is staging is actually hard. I mean, I did a lot of staging in my life, and or my group did a lot of work on staging, and it's a lot harder than direct style programming with a single stage. So to have to think of this happens in the first stage, then that happens in the second stage is hard. And the second problem is that monads don't compose, or should be more precise and say they don't commute. We can't simply swap monad constructors and expect the thing to work in the same way. So one has to do either higher order acrobatics like monad transformers, finary tagless, freer monads. It seems every couple of years there's a new one popping up that promises to solve the problems of the earlier approaches. Or what I see in the Scala land is increasingly popular. We just put everything in a single monad. We say a single monad is fine, but once you have two of them, you have a problem. So there's a monad with 3 type parameters, the resource, the error, and the result. And essentially everything has to fit that model. The problem is it's often over-provisioning. Sometimes I don't need an environment. Sometimes I want to do my own error handling separately, and sometimes I want to distinguish which effects I have. So this thing solves the composition or avoids the composition problems at the price of being very coarse. Industry experience so far with both approaches has been mixed, but from my perspective, I think the single monad is overall simpler to use and therefore more popular. So I think the people are sort of shifting to that back again. But there is an alternative. So the monads before, the effect systems before, they were popular because they solved a really hard problem, namely how to program with 1 million lightweight threads, so 1 million connections or things like that. The traditional threading systems on the runtimes couldn't keep up with that. So after 1,000 or so, you were done. So you needed something else, and because essentially the monads control what goes in a bind, that means the functional analogy of semicolon, they control what goes in every statement, they could add resource handling, schedulers, and things like that. So that's why we got essentially this reactive programming via the monads, and it was often the only choice. So that made them popular initially. But now we see that increasingly runtimes have coroutines or continuations or something like that that could also be used for this sort of asynchronous programming. For instance, in Java, Java 21 just got fibers, which are essentially coroutines, lightweight threads, which are called virtual threads. In more and more runtimes, we have something like continuations. So one could go back to direct style continuations or built on continuations algebraic effects instead of monads. And that's what I want to explore in this talk. But the questions remain, are continuations really simpler? So we still have to prove them to have a precise look. And how should we model control effects in the type system? A continuation is just a runtime mechanism. It doesn't really solve the problem that certain effects you can't mix in certain ways, or they mean different things and you want to exclude that. So how should we do that? So I take a step back and say, well, let's just put on our heads as programmers. We do error handling every day. What is your favorite error handling scheme? Is it some types like option or either with pattern matching? But if you do that, then decomposition is really a pain to actually filter out this error case or the none case at each step. It's a lot of boilerplates. So that's what monads were invented for, right? Options with monadic bind work much better, but compositions with other monads can be a pain, as we see. Or we eschew all that and go back to exceptions. But then the question is, should exceptions be checked or unchecked? You would think they should be checked. It's an important part of your contract. But the only language that seriously attempted that was Java, and it's generally considered a failure. It's generally something that programmers find a hassle rather than a help. And of course, unchecked exceptions avoid the hassle, but they are problematic because they just are essentially dynamically typed on that part of your contracts. Okay, so that's error handling. What about async computing, like futures, coroutines? Should we use callback futures? Well, callback futures coined the name callback hell, so yeah, maybe we should go on. Monadic futures are much, much better. That's what we have in current Scala 2. But again, composition with other monads can be a pain. How do I swap an option with a future? And maybe there's a list in between. That's sort of higher order composition operations. Async await is a simpler interface to futures, but it's very limited. It doesn't really work well with higher order functions. And coroutines are just too imperative. So what I would like for errors is something like this. So I want to say I have a list of options, and I want an option of list. So I want to just write optional, so that's essentially a prompt. And then I want to step through the list with a map, and I want to say, for each of them, pull out the option, and if it's okay, continue, build the result list, and finally it's a sum. Or if it's none, then essentially break out to the optional and return none. So basically early breakout if in the error case. Optional here is just in Scala function application. So colon indented block is just an argument to the thing. And optional is actually a module or an object in Scala parlance, which has an apply method which gets called. So this whole thing means the same thing as what you see here. And .ok is like .get, so it's essentially it gets the value in the option, but if the value is none, then instead of failing with an error, it will return to the optional prompt. And what you see here is that .ok also works in arguments of higher order functions such as map. So that's where essentially the simple approaches, they fail. For instance, in Rust ? I don't think I could do that, not unless map was inlined or something like that. And for async, I want something very similar. So for async, let's say here I have a list of futures now, and I want to wait for all of them. So I want to write, well, what I get back is a future, and I get the future by essentially mapping every future in this list with an await. I await for the result of each of these futures. And await also works in higher order functions. What I further want is often future spawns a new computation, but waiting and spawning a new computation don't really need to be related. So I want to say this await should also work outside a future block, but in that case I need a capability called async, which allows me to wait. So basically what you have is futures will generate that capability async, pass it down to the block, and the async capability is needed to await. And I can also separate the two aspects of it by passing the capability in this using block to some code that needs it. So using async is in Scala 3 an implicit parameter that gets passed, that gets synthesized by the compiler from what it has in the context. What I would like for errors plus async is just a combination of the two. So now we want to essentially await all results here. So we have a future of result. And I want to say, well, what we get is a future. And the future returns a result. And I've obtained the result by going through the list, waiting for all the results, and checking whether every result is OK. So if this looks a bit like algebraic effects, and indeed they're similar, they're very, there are a lot of connections, so you could say future and result are really a handler, or you could also say a prompt, and these things here, await and OK, are the effect which essentially interact with the corresponding handler. So the nice part of this is whatever we want. So all these things are super scary for essentially monads when you need to do something like this. But here, not at all. You just take the result type and you put the prompts in the order, in the handlers in the order of this type, and then you just do your effects, and that's it. So it's really baby code, nothing to think about. Okay, so that was too easy, right? There must be a catch, and indeed there is. So what about we flip the effects? So now we have a list of result of future, and we want a result of future of list. So essentially, we pull them out in a different order. So we write result, future, and then the same thing, but since we have a result here, we do the OK first and the await afterwards. Really? That makes no sense, because what would happen here is result is some things is OK with a value or error, and basically when we form the result, we have to decide what it is. But in a future, that's a delayed computation. That's a deferred computation, so we don't know what it is. The future will compute. Or what would otherwise happen is the future would, when it finds the first error case in the OK, it would say, oh, no, we have to abort everything and back out to the result. And that's often not possible because the future might actually run on a different thread. So you're talking about exceptions or aborts crossing threads, which is complete anathema. So you don't want to do that. So this shouldn't work. And so we want a type system that says the former thing is OK. So this one is fine, but this one should be an error. So what could that type system be? So before I go into that, I want to just look at the 10,000-foot view to say, well, the problem we have is monads don't commute. Effects in general don't always commute, but there are effect pairs that do commute. Capabilities as arguments, like what you've seen here with these async things, they do commute. It doesn't matter in which order I get the capability A and capability B. The end result is I have them both. The order doesn't matter here. But not all combinations of handlers make sense. So we've seen one combination that didn't make sense. And I want my type system to flag an error when they're introduced in the wrong order. And the idea that we've been working on is to use capabilities to describe these effects. Okay, so the capability-based architecture then would be one stage only, no staging. I can use everything the computer can do, so I have my purely functional code, but I also have all these other things. But everything which is not purely functional is under a lock. I need to have a capability to be able to access these things. So that gives you also essentially a distinction between a purely functional program and an effectful program, but now the distinction is whether you hold or get past the capability or not. If you don't have any capability and nobody passes your capability, you're forcibly a purely functional program. You can't do anything except doing lambda computations. But once you have capabilities, the capabilities tell you what you can do. So that's this view. And that is actually a very, very old view. It was first proposed by Jack Dennis and Earl Van Horn in 1966. Jack Dennis is one of the founding members of WG 2.8, of which there are quite a few members here. So what does the object capability model define? It says capabilities are regular program values. They're just variables, parameters passed around. And you can create them, that's what they call parenthood. You can pass them to object constructors, that's called endowment. And you can pass them in messages, that's called introduction. And when an object has a capability, then it can just use that indefinitely. The advantage is there's no new language feature. In fact, we give up a feature, we remove a feature, and that feature is non-local variables. You can't essentially hide a capability in a variable and pick it up by somebody else. At the same time, it's quite powerful, and it has a proven track record in security. But it hasn't taken over the world exactly, even though it is quite popular. And why is that? There's some things missing, I believe. The first thing that's missing is capability revocation. Once somebody holds a capability, they can never need to give it up. And that's just not how systems work. For instance, capabilities for us are typically have bounded lifetimes, or they have constraints such that they can't be shared, or things like that. So capability revocation isn't solved by this model. And the other one, which is probably more significant in practice, is that passing all these capabilities around in parameters can get really tedious, right? Everybody needs to get 3, 5, 6 capabilities. If they're all separate parameters, oh my God, that program will look pretty much like a mess. So the original object capability model is untyped. The types don't enter the picture here. It's essentially something that works without types, but types can bring important improvements. The first is with using types, you can define what is an implicit parameter, a parameter that gets essentially passed by the compiler if there is a certain type signature of the function. So that avoids the tedium of having to pass all these capabilities explicitly. And type systems, if we push them a bit further, can also enforce resource constraints such as lifetime and sharing. So what we use capabilities for are effects, control effects, but not just them, effects in general. So what do capabilities have to do with effects exactly? So I just have a simple example. So this is clearly an effect. I could use a monadic thing, exception of t, but here I just do the old Java thing. I say, well, the function returns a t, and it also can throw an exception e. So that's clearly an effect. The capability view of that would be this. So it says the function, it returns just a t. I don't say there's nothing that I do with this type constructor, but it needs the capability that it can also throw an e. And the two things are morally equivalent, or To make the point, you could even go more fine-grained. You could say, well, here we have this thing. So this T throws E is really just a type. It's an type-written infix. It's called throws TE. So now we have a type that contains the effect. And throws in this implementation is just a type alias for what in Scala we call a context function type. So it's a function from can throw to T, but it's a function that's applied implicitly. So whenever somebody has a function like that and uses it, then the can throw thing will be synthesized by the compiler. So F is this implicit function type, and that's really the same as writing it out and giving it an implicit parameter. So all these things were explained and explored in a paper in POPL 2018 that I reference here. But you could say, yeah, okay, but isn't that just a game of syntax? Why would any of that matter? You're just pushing symbols around. Well, the thing that we solve here, or can address here, is a problem that has been a very long-standing problem in effect systems, which is called the effect polymorphism problem. So what is that? The effect polymorphism problem comes from the observation that unlike other types, effects are always transitive. So if I have a calling chain from F1 to Fn, say, and Fn has some effect, then F1 will have the same effect. And the problem is that if this calling chain is dynamic, so there's some higher order functions and I don't know statically what they will be calling, then how do I describe the effect of F1? And the answer is typically I need to introduce a lot of type variables to actually express this behavior. So let's look at a very simple example. That's the map function. That's sort of our lab rat, which we use for everything, right? So the map function on lists on Scala looks like this. So it's defined in class list. It's a map. It takes a type parameter B and a function from A to B and returns a list of B, right? So if I wanted to express effects in a traditional effect system, then I'd need something like that. I need to introduce a second type parameter, E, that's the effect. And then I have to say something in the result type of that function that it returns a B and it also has the effect E. And then that same effect is the result of the map. And that effect could also be a type constructor, so that includes monadic effects where essentially the structure is a little bit different, but it's roughly analogous. Okay, so that's the effect picture. And you could say, well, that's okay, that's not so bad. But it really is. So the problem is that a function like map is prototypical for almost everything we do. In functional programming, there are lots of functions that take higher order functions. In object-oriented programming, essentially we have virtual dispatch everywhere, and it's exactly the same problem. Virtual dispatch, we do not know what exactly we call, so we have to parameterize the effects. So what would happen if we did this thing everywhere is a sea of effects. Another argument why this is really not okay is this actually works in Java. People don't know that, but it works something like that. You can have variables that range over exceptions, over checked exceptions. Nobody's using that. Absolutely no. Everybody works around because it just gets too painful, all these effect handlers and parameters. Okay, so with capabilities, what would map look like? Why would it look like this? White. That's exactly the same that we've written up here. So what goes on here? So how can you essentially just sweep them under the carpet? Well, we can sweep them under the carpet because this type A, double arrow B, is now the type of impure functions that can capture any capability as a free variable. Functions, closures, so closures close of an environment. The environment can contain capabilities. There you go. So it's not map that needs to be past the effect handler or that has the effect handler. Map just says, I call this function and this function could have capabilities or not. I don't care. The algorithm for map is always the same. Well, there is a concern which says, well, if we have, let's say, a parallel map, then we probably cannot handle arbitrary effects in the argument. So we want to enforce purity. And for that, we now have another function arrow, A single arrow B, for pure functions. So this, we played in Scala a very long game, 20 years, to say we reserve the single arrow for purity for the time when we catch up with OCaml and Haskell. And there it is. So the double arrow was always the thing with the effect for. Yeah, I wish. Okay, so let's look at this in a complete example following the exception analogy. So we have here a function, an exception, let's call it too large, a function that might throw too large and otherwise return an int. So it throws too large when if x is greater than some limit. And then we have a try, which catches that exception and otherwise maps this function over a list and generates the sum. And the handler would say, well, if one of these things returns with the exception too large, then we just return -1. So if that's the effect view. If you look at the capability view, and that's what the compiler makes of this, you could say, then it's these green things in comments. So to say, instead of the throws thing, we have this using can throw. That's a capability. And where does it come from? Well, the try generates it in here in the middle. So because we call a function, it needs a capability. We're in a try, so we have a handler, so we can generate that capability. We pass it to the function. The function here, that's the lambda, it starts here. It closes over the can throw too large. You see, can throw too large becomes a free variable in this thing. And that's why map doesn't need to be concerned. So it closes over the too large, and map just says I just take any function I want. But we're still not done yet. This capability, we observe that this capability has limited lifetime. It's not just a value we can hold on indefinitely, like in the OCAP model, because once the try is done, the handler is done, and we can't use this, we shouldn't be able to use this can throw anymore, right? So here is a problematic example. It's almost the same as before. It's just that now I don't map over the list, I map over an iterator that ranges over the list. So an iterator delays computation, right? It will give you the elements successively when you call next. And we call next the first time after the try catch. So what would happen then is, even if one of these elements in the list is too large, nothing would happen here because all we return is an iterator that hasn't done anything yet. And the first time we do next and hit an element that's too large, we throw the exception, but there's no handler anymore, so it's an unhandled exception. And that counts as essentially one of these programs that go wrong that our type system should have caught, only it didn't. So what we need to do here, so that's essentially the pay up time to say for all the flexibility and freedom we got by passing effects as parameters, we have this new thing. We now need to track in a type which capabilities can be captured by its instances. So that's the price we have to pay for it. To condense it a bit further, I do the same thing, but a little bit simpler. So now I have a try with resources pattern with a file. So essentially, I have a with file combinator that I can use like this, with file f.write OK. And what with file would do, it would create a log file. It would, sorry, this should be body. It would pass it to the body. It would close the log file, and it would return the result. And here we have the same problem that we have to do everything with the file inside the with file, because afterwards it will be closed and we can't use it anymore. So the problematic case would be something like this, where we write with file and we have a closure that says, hey, f.write, I'm late. So that wouldn't work because we return the closure, and by the time we call the closure, well, the file is already closed. So what would happen in order to exclude this, all you have to do in the new version of Scala that we're working on is to write this little hat here behind the file. The hat says, hey, this thing is a capability, please track it. And if you do that, then what you would get here is an error message which says a local reference leaves into outer capture set of, it would say type parameter t of method with file. Don't worry about the precise errors, we have to improve them, but there is an error, that's what counts. Okay, so what's a type system that does this? So the idea is we need to track in a type which capabilities it captures. So what we do that is we use the hat and then a set of capabilities. And what is a capability? It's just a reference to a program value, a local variable or a parameter or something like that. So it's not something like an extraneous thing like a region. It's really something you have in your program. That's the object capability idea. But it's not all of them, because that would basically track all the free variables of a closure. It would be far too detailed. So a capability is a capability because it has a capturing type with a non-empty capture set. So that's what I referred to before. Anything that has a capturing type is a capability. So it's self-recursive, right? So you have a capturing type that contains capabilities. That's why you're a capability. So it has to end somewhere. So there's a root capability cap from which ultimately others are derived. So cap is sort of like object in an object-oriented system. So we have some abbreviations. So you saw this T hat. That's just a shorthand for T hat cap. So it's the root capability. We have some abbreviations for function types. So because this thing is a bit clunky to write, we just put the capability directly after the arrow. And the A double arrow B that you've seen is a shorthand for A cap B. So it's a function that can do anything. Okay, so that now we are ready to do just a little calculus. I'm giving you sort of the abbreviated version, simply typed version first. So we have just a simple type lambda calculus. It's in monadic normal form, so that's just a technical detail. So we can apply only variables to variables, and to make up for that, we have a let, which is primitive, so that lets us build more complicated terms. We have now functions that can refer to their parameters, so we need dependent functions, or at least some form of light-weight dependencies. So a function type looks like this. It has a parameter x that can be referred to in T. And the type is one of these shape types, or it's a type that contains a capability set, a capture set, and a capture set is just a bunch of variables. So that's the simple syntax, and if we have a shape type this with an empty capture set, then we just write the shape type. Okay, so one thing we need is, so this whole thing needs subtyping, which makes sense because capabilities are sets, and sets have natural set inclusion, so that way it comes in. So we need to define a subtyping-like relation on these capture sets, which we call subcapturing. And subcapturing has the set axiom, so smaller sets lead to subtypes, which means that pure types with empty subsets are subtypes of capturing types. So a pure type is a better type than a type that can have effects. That's our subset axiom. And further, we have this other thing which says that if X is declared as a type with a certain capture set, then X becomes a capability, and the set consisting of just X is better than the capture set under which it was declared. So that rule says that derived capabilities are more specific than the original ones, and therefore every other capability is more specific than cap, because ultimately everybody is derived from cap. Cap is the biggest capability. So to see an example, let's say we have a function proc with a capability IO, and another function which is a proc which refers to this function, which now is a capability because it has I/O, and is also async. Then we would have that the set G subcaptures the set F and async, because it was declared that way, and that furthermore subcaptures I/O and async. And if we instantiate that to pure types, we get this idea that essentially variables that are not capabilities, we don't need to track them, because if X is a thing with an empty capture set, then by this rule, we have that the capture set of X subcaptures the empty capture set. So it's equivalent to the empty capture set. We can just drop these things. Now, if we look at the typing rules, then I see it didn't come out well. Okay, so there's some underlined gray, so I'll circle that with the marker. So this is basically just a version of simply typed lambda calculus with subtyping in the paper that appeared in Toplas and Popple, was presented Popple this year. We extend that to full F sub. The new things are very, very small. So the first thing is the var rule has this special provision to say that if X is a type that captures a certain capture set, then if you refer to X, you get, the question is, you get the better capture set X. You say the capture set of that is just X, because X is a capability, instead of the other set C. So you get a better one, but you can get back to the original one, of course, always by subsumption. So because we have established that X in this case is subcapture C. The second set says if you have a lambda, then you look at the body of the lambda, you look at the free type variables, the free variables of that body, you deduct X, because that's the parameter, so every free variables of the lambda become the capture set. And those free variables that are not capabilities can be dropped by the rule that I've shown you before. So in the end, you end up with a capture set of just the capabilities. And the last change is in the application rules. So if I have now a function which has a capture set of capabilities, and I apply it to some argument, then what I need is a dependent application, because essentially the T2 might refer to Z as a capability, so I have to rename that to Y. And otherwise, the capture set C gets dropped, because the function is now used. The capability is not retained. I don't need to keep that into account anymore. Okay, and then in the let rule, we have the typical let rule where, since we're now in a dependent type system, we have to make sure that the local variable is not in the result type T2. So that if that happens, then we use again subtyping to widen to a type that doesn't mention this local type variable. So that the let rule might force widening for avoidance of local variables. Okay, so that's that. What about polymorphism? Can type variables range over capturing types? And it turns out if they could, we'd need to introduce type variables in capture sets, and that would make the whole thing a lot more verbose. So we have an alternative that's taken from modal logics, where we introduce, I went too far. Introduce box types. So we have a box in front of TC, and these types count as pure types. So they hide the capability set in the type. A boxing operation then of a term would produce such a box type, hiding all captures, returning a pure type. And there's a dual unbox operation which would reintroduce the hidden captures. And this boxing unboxing is very closely linked to type variables. We always box when we go into a generic context, and we unbox when instantiating. And otherwise, box, unbox are not programmer available. So they're essentially a mechanism that we link with type variables. And it's actually very similar to boxing and unboxing in the erasure model. When we use erasure, it's basically the same thing. Okay, so what this gives us is a very convenient thing, which I call capture tunneling. So here we have a class cell with an element, and let's say we want to build a cell with an A which captures something. So the question is, should B, the cell, capture the same thing? That would essentially propagate a lot of captures into a program, and the answer is no, it doesn't. B is just of type cell, and the thing is inside, but there's no capture on the outside. And the way that works is because the compiler has inserted a box operation here, which creates a box type which hides the thing. And then if we access the element here, b.elem, at that point we have to unbox it because we need a T and we have a box thing here. And the unbox operation would reveal the capture set that's in here. So if I put the whole thing in a closure, then the closure would count as, even though it doesn't mention C at all, it still counts as capturing C. So that gives us this capture tunneling. When we construct data structures, we hide all stored capabilities inside the structures. When we access data structures, they pop out again. And that turns out in practice to be really, really important to keep the notation small. Okay, so the last thing to explain is escape checking. So we had this with file with problematic thing. Why didn't it work? So if we look at the with file application here, so here that's the body. We have a closure that writes I'm late. So that would be a function that captures F, because F is outside this inner closure, right? So the type is empty parameters to unit capturing F. So the whole thing inside with file would have the type, it takes a file, which is a capability, and it returns this function, capturing F. So that's a dependent function. We have a parameter here, and it appears in the result, which is the thing behind the double arrow here. And the problem is that with file, if we look back at the type it wanted was this, file had to T. So there's no dependency that's allowed. This is just a regular function type. So we have to widen this up to become a parametric function, which is not regular. And the best thing we can do is to just say, well, make it cap, make it the maximum capability, because that's the only way to avoid this F in the type. So its parametric supertype is file hat to empty parameter to cap unit. So T, the T part, gets instantiated to this thing, which is empty to cap unit, which is essentially contains this cap capability. And now there's a rule that you can't put cap in a box. So that gives us the escape checking. You can only put variables in the environment in a box, and cap doesn't count to be in the environment. It's sort of a meta variable. Okay, so the current status of the project is we are about a good year into the 5-year project called Caprese, Capabilities, Resources for Effects. And we have tried capture checking already in some areas, the Scala 3 compiler itself, with the goal of arena allocation for contexts, the standard library, which is now almost completely capture checked, and a new library for direct style continuation-based concurrency and I/O called Gears. In practice, you can turn on capture checking in Scala today. You just need to use the latest version, and you need to add this dependency to get the capture checked library. The standard library that we ship by default is not yet capture checked. So this thing is, and so you have to put in a dependency on that thing here instead of the standard one. And you have to turn on an import language experimental capture checking. So the experimental should be a key, an indication for you that, yes, this is still quite rough around the edges, so be gentle with it, or not, and report bugs. Okay, so the experience so far is that the notational overhead is very reasonable. For instance, collections like strict list or map do not need any additional annotations in result types of operations. So in particular, the fact that we could take the standard library and make it capture checked without changing the bytecode. So this is just type annotations. It's exactly the same standard library is a sign that this actually works pretty well. Lazy collections such as iterators do need some annotations, but these are generally what one would expect. So here's the example of the list API. I've left out overall, there are more than 100 methods, but basically they're all the same. They're all the same as before. The only thing where we see these hats here are things that we could also have dropped, but they give you a bit more flexibility. So for instance, in the ++, that's concat, we give you an iterable once, which is could be an iterator or a collection as the second argument to append. And we say that thing can be side effecting. That thing can hold capabilities. It doesn't matter. We will all essentially discard them as we step through the list and append through the list. So those capabilities won't show up in the result. And we have also fine-grained control whether arguments should be pure or can be impure. So here, map says our argument can be impure because that has been like that in Scala forever, but we could add a pure map that says we only work with pure now, and that could, for instance, work with parallelism. Now, if you look at iterators, we see that by and large, a lot of the methods are still the same, but transforms of iterators get capture annotations. So if you look at map on an iterator, that's different from map on lists because it says it gives you back an iterator that retains the current iterator this, because, well, it's just a closure that needs to refer to this iterator, and it also retains the possibly side-effecting function. So those things are things that are part of my result. And the same thing for other transforms like flat map or concat. So these are actually, I would argue, these are actually helpful. These are good things. If I do sort of fancy things with closures and effects, I want to be told what kind of closures and effects I have, right? Okay, so now I'm almost out of time, but I still want to give you a quick run through with capabilities for control specifically. So let's come back to control of abstractions, and I want to show how capabilities can support a wide range of these things in a simple and safe way once we have delimited continuations. So we need to build on that for the more advanced capabilities. So as a warm-up, we do boundary break, which is just essentially an alternative to non-local returns. So if you look at, if you ask students, then a typical task is find the index of the first index in the list where that contains a certain element, and well, they want to do a for loop, and then they say, well, how do I break out of a for loop in a functional language? I don't know how to do that. You have to use a fold. Oh my God, first course in functional programming folds already. So, here's a simpler alternative. We just write boundary, which gives essentially a prompt, and then we can break to the boundary with a value. So it's not like for loop breaks where we just get out, we break with a value. We return a value to the boundary. So it looks like this. We In the stack, we define a boundary, then we do something, and we can break out here, and that would return a certain value into the slot of the container. And that's written very simply by saying, well, what we need is we need a class label, which essentially gives us the boundary. And to break, you need a label. And the label is tracked. It's a capability. And you break with a value. And the apply method, so that's the thing that takes the thing that's in the boundary. It would just synthesize a label and pass it to the code that uses that. And to break out, we use efficient code when we can. So if we are in the same stack frame, the boundary and the break, then it's just a jump. And if we are some stack frames down the calling chain, then it's a very fast exception. It's a fast exception because it doesn't need to capture a stack trace. Why does it not need to capture a stack trace? Because we know it won't fail. We will, even if it would capture a stack trace, we would never see it. We have a handler. We know that we will return to that handler. Okay, the next thing is error handling. So that's what I wanted for the error handling thing. So here we have a thing like that. So we have a first column. So we have a list of lists of t's. And we want to get the first column, the list of all the heads of these lists, provided they are all non-empty. If one of them is empty, we want to return none. So what we write is optional. We go through the list. We take head option, which gives me either the head in a sum or none. And we run OK on that to say, if it's none, then back out to the optional. And how do we do that? So how does that work? Well, optional has, again, an apply method. That's what takes the body. So it just runs the body. And it wraps it in a sum, because when it ends with the body, well, then we have produced this list. And it passes the whole thing to boundary, what we've seen before. And what is OK? So OK is a method on option of t, but because option of t is in the standard library, which we can't touch, the Scala 2 standard library, we add it with an extension method. So if we add it from the outside, so OK needs a label. And what we need to pass in the label is none, is the none object. So that's the type of the label. It needs a label, and if the value, the optional value here is defined, then it gives you the optional value, and if it's not defined, then it will break out with the none value. So the body is an implicit function, a context function that needs this label, and that label gets generated by the boundary. Okay, so next step is suspensions. So far, we've just aborted a part of the stack. So what if we could store the stack segment between a break and its boundary and reuse at some later time? So we have this suspend thing, and what we want to do is we want to say we have this block, and we want to just move it elsewhere or keep it in place and shift our focus elsewhere. And that thing is a suspension or a delimited continuation. So our API for that is this. To say we have a suspension, which is essentially another word for delimited continuation. And what you can do with a suspension, you can resume it. And then we have a function suspend, which takes essentially a body that we pass the continuation, the suspension, and you can do something with it. And that suspension will essentially store it away or do something and continue. So suspensions are frozen computations that can be subsumed. And as we know, these delimited continuations, we know since Zielinski, are quite powerful. They can express at the same time monads and algebraic effects. So let's see how they express algebraic effects in this framework. So as an example, I want to do Python-style generators, where you essentially just go through the thing and return a bunch of values. So a generator is just a function with next option, which gives me either the next value or none. And what I want to do is I want to use it in a program like this, which is actually more than what Python can do. I want to, let's say I define a tree of leaves or inner nodes, and I want to give you the leaves of that tree. So what I want to write is something like this. I want to write a method recur that says, well, let's step through the tree. If the tree is a leaf, then produce that leaf as the next value of my generator. And if it's an inner node, then recurse for each of the children. And Python can't do this because this only works in a single stack frame in Python, whereas here I recurse through the tree. So how would I do that with a generator? Okay, so the first thing I need to do is I need to essentially pass something implicitly down that represents the boundary of my suspension and wraps it in something else. So I need an effect type. So here the effect type is this producer trait, and that has the produce method. So produce was called outside the trait, so that's simply saying to have a global produce, I need a producer, I get that implicitly with a parameter, and then I just call the produce of the producer. Okay, good. So now we have the prompt, the generate thing, which contains the body. So it gets a body with a producer to unit, and we have to create a new generator. That's our return type for generate, where the next option method is implemented by calling a step function called step. So what is step? Well, for step, what we need to do, we need to say step is we run the body of generate in a boundary. The way we do that is that we create a producer, and the producer is available as an implicit value. That's this given here. And what does the produce method do? Well, it takes, it suspends, it takes a continuation, and it says, well, we return the value that we got, the inner sum, so that's the next value, but we store the continuation in the step function. So the next time you call step, you will essentially run the tree again with the continuation. So that's how we can thread the values through the tree. And so that's the producer that does that, and otherwise we just essentially run the body and at the end return none to say, well, we're done. So to see the relationship with algebraic effects as a summary, effects are methods of effect traits, and handlers are implementations of these effect traits. So the effect was this producer, and the handler was this given here. So that's my handler here, that essentially has an implementation of this produce method, and the handlers are passed implicitly. So I can do something if I have a handler, and implicit parameters take care of essentially that I don't need ceremony to do that. And what a handler can then do, it can abort part of the computation via a break, we've seen that, or they can suspend part of the computation as a continuation. So that's a different view of algebraic effects, which I think is called lexical, it's lexically scoped algebraic effects. So it's a quite a standard view that I just wanted to use with the Scala implementation. But we have to contrast it with the other view, which is sort of the exception-like view, which I think the latest OCaml follows, where essentially you have this free algebra of types that you produce and catch. So in the exception view, where essentially algebraic effects are resumably exceptions. So, oh, sorry, what did I do? In that view, somebody throws an exception, somebody hopefully handles it, depending on whether these things are checked or unchecked. But even if they're checked, we don't statically know what the handler is. It could be something else on the stack that intercepts the exception. And that gives you more power and flexibility, but it also gives you more unsafety. So it gives you fewer guarantees, whereas with the continuations view, essentially, you have this continuation, it will be this continuation that will be called 100%. So there's no way to essentially smuggle something into the stack trace. So it's a bit akin to dynamic scoping versus static scoping for continuations. And to just quickly wrap it up, the last thing is async with futures. So what we want to do with futures is write something like that. We want a future, and we just have this universal await method. So futures can be nested. So here we have two nested futures, which just read both of them from a channel, both of them await, and we can sum the results and go on with that. So simple futures are just an evaluation mechanism, and actually here I have to go back to Arvind, because he pioneered this. He called it lenient evaluation. That is, that strict evaluation is you evaluate as soon as you define. Lazy evaluation is you evaluate at the latest possible instant, when somebody needs your stuff. And lenient is you evaluate at any time between those 2 points in time. And that was used for parallelism. As just an evaluation mechanism, we shouldn't do any monadic ceremonies for this thing. So if your program is pure, you want to use parallelism just for computation, then of course you want to write it in direct style. But in general, nowadays, futures often do encapsulate some effects because they interact with I/O. And interacting with I/O means that you need, when you do a wait, you might have to wait a long time, a very long time, maybe indefinitely. So that should count as an effect. And the other effect is you actually need to, in the structural concurrency model, you need to cancel these futures if they're no longer needed. So that should also count as an effect. And what we want to do is essentially use that in a very lightweight manner to say, well, the lightest way we know for an effect is a capability, and that for us is the async context. Now, what I am skipping over is this gears thing, which is the project that does all this. So I'll publish the slides, and you can look it up there. But essentially, what the end result is, what I promised before in my ideal thing that we should catch these things, we actually do by the capture annotations in gears. So basically just say, well, okay, he ran out of time, but he promised us in the beginning that he can do certain things. So here's the backup of this thing. So here's a function that couldn't have been implemented. And it couldn't have been implemented, because essentially there's a capability that escapes its scope. Very similar to the with file example that we also see again. Okay, so let me finish and just go quickly through related work. So capabilities, of course, are also a very old thing in type systems, going back at least 25 years. But in type systems, they were by and large used as an extra thing, like regions or something like that. They were an extra ingredient of your type systems, and they tended to make your type system more powerful, but also more complicated. By going to object capabilities, we say we use something we already have, namely plain parameters, plain values in your program, so we become simpler. Systems that use this view of object capabilities, there are a couple of others, notably there's Effect by Jonathan Brachthäuser that has the same viewpoint, and there are also reachability types by Tia Grompf and his team in Purdue that has a similar philosophy in slightly different application areas. The whole thing, the theory has been written up in a paper, Toplas 23, and what we have also done is to extend this to separation checking, so to control sharing. There will be an upcoming paper at Uppsala. So to conclusion, direct style structured concurrency is back, and capabilities can make it safe. Capabilities can model algebraic effects, and they naturally enable effect polymorphism. And the ingredients you need in a language to support that are some form of implicit parameters to avoid the tedium, and some form of path-dependent types. That's all you need to track the captures. So Scala was well positioned to pioneer this because it already has those two things. So essentially, we put them to good use here. Thank you.
Thank you, Martin, for a very nice talk. We have time for just a few questions. If you go up to the microphones, please, to ask your question. And state your name before.
Leo White, Jane Street. Great talk. So I was wondering, so the dependency that you have here is not like true dependency. I think it's fair to say it's essentially the same dependency you get in an SML module system or similar, right? And I was just wondering whether you had done anything to, whether you tried to do something similar to the effing modules translation, kind of translate out the dependency into something that had like regions and region polymorphism instead?
We haven't tried that. It would be quite different. So, so if I look at like typical region-based type system like Rust's, then they embody a policy. So they say, okay, so we have these things and they have to nest, and you have borrows, which says, essentially it's a policy. You say you have this move semantics underneath, and then you can borrow and things like that. In the capability world, all we do initially is just describe how things are. We just say, okay, this thing hangs on to this, and this thing escapes here. And the policy aspect to say certain things can't happen, like you can't put cap in a box and things like that, that comes sort of as an afterthought afterwards. So it's sort of, you can do similar things, but the approach is different. So the core of capabilities are purely descriptive, you could say.
Sure, thanks.
Yeah, I guess my question is somewhat similar, so maybe I'm rephrasing what Leo was asking. So it seems like in none of your examples, like it always was the case that the capabilities are just like passed down as parameters to something, and in none of the examples they were kind of like stored away or returned. So would it be possible to, instead of making them like first class values, model them as a second class thing, which would allow you to not have this high pay-up of implicits and dependent types potentially? I think that was what Leo was referring to, with like a regional kind of like
actually, that actually was tried. That was 2016 OPSLA second-class values. That, I think, was a predecessor of the reachability work at Purdue. It is quite restrictive. And actually, I did show examples, maybe not complete examples, where these capabilities do show up, and it transforms on iterators. So you have an iterator and you have a map. You do a map on an iterator. Well, that gives you a new iterator, and you have to say what it hangs on to. Otherwise, you couldn't write that. You couldn't write anything that returns a closure that hangs on to capabilities.
But it could still hang on to a second class value, a second class thing, right? That doesn't necessarily mean it has to be first class, or maybe...
Well, second class you can only pass down. So if I write map, then the result of that is it goes up a little while, a little bit, like to produce this value. So second class values don't let you do that.
Okay.
So what we want to do is essentially local, even if they're scoped, we want to do local construction of these things, and then we want to ensure that the whole thing doesn't escape rather than have this strict discipline that every value has to go down.
Okay, thanks.
Hello, Adam Chapala from MIT. You had an applause line about how you'd introduced the pure function arrow that folks are familiar with in other languages, which basically allowed declaring that capabilities are forgotten for some subcomputation. What I wasn't clear on is whether if some code drops some but not all the capabilities, like I was in async and option, and I'm going to temporarily forget the option part, whether you have the right type system features to track and enforce that.
I had a problem getting it from the audition point of view.
Okay. You talked about how it's possible to write a pure function type that records the fact that you haven't captured any capabilities in there. If we wanted to be finer grained and support a pattern where basically I'm inside multiple monads and then I leave some but not all of them for a subcomputation, is that supported by this type system?
That is supported, but it would be more complicated, because in that case, what I think one way to do it, well, either you have a fixed set that says, okay, a function type that can just capture this and this and this, I give you an upper bound, so that would be fine. Or I can pass this through the map function. So I can say the function takes now a function that takes some capabilities as additional parameters that are provided by the map. So yeah, we can do all these things, but they become a bit more complicated.
Does the client code that uses that function look more complicated, or is it just complexity in the library implementation?
Depends on to what degree you assume type inference. Probably you can hide them pretty well, yeah.
Okay, thanks.
But there's a sharp edge to that, right? So as we know with error messages, when things don't work out and you have complicated types in your functions, I
think we'll just take one more question because we are over time.
Clemens Greik, University of Jena. I wonder how at least the basics of this relate to uniqueness typing in Clean. How the basics, the foundations of this work relate to uniqueness typing.
To what?
Uniqueness typing.
Uniqueness typing. Uniqueness typing is one of these frameworks that uses, there are uniqueness, so for instance, my former PhD student, Philip Haller, he had a uniqueness type system with capabilities. But those were the capabilities that are essentially in the type system. So there were other things that the type system kept track. They were not program values. So for uniqueness typing and program values, the closest published things are probably reachability types. They're fairly close to that. They follow this philosophy and apply it to something like uniqueness typing. Yeah.
Okay. Thank you.
Yeah.
Okay. Thanks again, Martin, for a very engaging talk.
Thank you.